So today's lecture is on optimization. So this is Unit 11, lecture 1. And we're going to see optimization in 1 and n dimensions, and we're going to do a little bit of sort of practical tips for debugging functions. A lot of optimization is uh, basically constructing Python functions and then optimizing them. So this is more for if you're reviewing the lecture notes about what are the goals of this lecture. So let's start with root finding. So optimization includes both root finding and minimization and maximization. So root finding is basically finding zeros of a function, but root finding more generally allows you to solve any function because any function where you're trying to solve for a variable can be rearranged so that you can solve an arbitrary expression. So for example, here's an equation which has no analytical solution, cosine x of x equals x. But if I rearrange it to be cosine of x minus x equals 0, then now this has become a root finding exercise, and now I'm just trying to find what are the zeros of this function. So one of the most common, or probably the first method for finding roots is called Newton's method, and we can use that in Python. Now we're going to talk about Newton's method, and it's kind of just an example to motivate some of the discussion. Newton's method should not be your first choice for finding roots. There's a function called root, which is a little bit better and more appropriate, but we'll just look at Newton because it's a nice simple function for examples. So the tricky thing, or I shouldn't say tricky, but the special thing about root finding and optimization in general is that you need to pass in a function to the optimizers. So Newton is a function which takes in a function and it will find the zeros of your function. So the first argument to Newton is a function. Now, you can pass functions a few different ways. One way is to define a function using the lambda keyword. And we'll see a little bit more about this. This was covered in Unit 10, or is that right? Unit 9, Lecture 2, I think, and we skipped over this lecture. So I'll just review it briefly. Actually, I think I'll just review it briefly over here. So we want to be able to pass functions. So one way we can do this is using the lambda keyword. So what the lambda keyword does is it creates a function for us. So lambda says I'm going to create a function. Why is it called lambda? Just historical reasons. It could easily have been called like, make function, but it's called lambda. Then you have the arguments. So this is a comma separated list of arguments that your function takes. So let's do an example with two arguments, x and y. And then you need to put one line of code and that will be returned. So we don't need a return statement, we just have one line of code. So like x times y. So that's my function, okay? Now, here's the thing, is that the point of being able to do lambda is that it allows you to create a function without naming it. So they're called anonymous functions. So this is called an anonymous function. That is, there's no name, right? So I can pass it to another function. So like here, I can pass this to another function, but I don't have to take the time to name it. Now, just to demonstrate it, I will set it equal to a variable and then use it. But this is not how you typically use anonymous functions. Usually they're just used to create a function quickly without having to come up with a name. So if I do that, it demonstrates it. So it takes two arguments, x and y, and then it computes the product of them. So the special things about lambda is that no name can take any number of arguments, but no defaults. We can't do defaults, right? Like we can't do like y equals 2 or something. And then one line, which is returned. No need for a return value. So like if we had another function like b that takes in two values and we want it to be the same, we would have to write return x times y. That's how we would normally do this, right? So just basically you can omit the return. It's one line function and it takes comma separated arguments. Okay, are there any questions on lambda functions before we move on? Okay. So here I have the lambda function cosine of x minus x. That was this function we're trying to find the root for. We're trying to find this to be equal to 0. Notice I don't have to tell Newton that I want it to be equal to 0 because, right, Newton finds roots, so there's no need to specify that this should equal 0. The second argument is x naught, and x naught means where I should start my optimization. So Newton and all these methods, they're iterative. That means that they basically start from an initial guess and then improve it. So you can tell Newton where your initial guess is. I chose 0. There's nothing special. You could have chosen 1, you could have chosen 10, you could have chosen minus 10, whatever you want. I just chose 0 because it's a nice, easy guess. Then Newton returns a result. I called it root, okay? Then I just printed it out. Turns out cosine x equals x at when x equals 0.739. And then I just verified that it is indeed a root by checking does cosine of x minus x equal 0. Okay, are there any questions on this example? All right. So the way Newton's method works is something we actually covered when we were discussing eigenvalues and eigenvectors. It basically starts with an x0, and then it updates to come up with xi plus 1. So x1 is being equal to x0 minus the function value at that x value divided by the derivative at that value. I'm not going to spend too much time on the intuition for that, but basically it has to do with finding a line, a tangent line, and then using that tangent line to go closer to 0. So you can see here working on just an arbitrary curve. Basically, it finds a tangent line and uses that tangent line to head closer to 0. Right, so it says, okay, the derivative says the 0 is this way, so we head down that. So that's all that's happening in Newton's method. Okay. So now because this is iterative, you can actually change two things. One thing you can do is you can say what is the tolerance for error. So I can pass in a TOL equals 1 times 10 to the minus 3. That tells Python that I only want my answer to be accurate to 3 digits of precision. Or sorry, not 3 digits of precision. I want my answer to be accurate within 0.001 of 0. What this does is basically sometimes an optimization can take a long time. Like if your function is expensive, like maybe, cosine's a pretty cheap function, but let's say you had a matrix inverse occurring in here, then you might want to have a lower tolerance so that your function can be completed in a reasonable amount of time. In general, they have very good defaults, so you don't really need to modify it too much, but just you can be aware of how this thing works under the hood is that it has a certain tolerance and it has a certain number of iterations. And that's the other thing you can say is what's the maximum number of iterations you will accept. So you can change the tolerance and you can change what's the maximum number of iterations. And that basically controls how long the Newton method will work to find a root. So like I said, Newton's method is just sort of for instructional purposes. It tries to find zeros, and it works for continuous functions. We haven't talked about it yet, but basically there are optimization for continuous variables and discrete variables. The variable we're optimizing is x here, and so it's continuous. X was continuous, right? We're doing cosine of x, so it's continuous. And it works for one dimension. You can pass in the derivative. So I didn't mention this, but basically you see that Newton's method requires the derivative. It estimates it numerically. So it basically tries perturbing x a little bit up and a little bit down and uses that to estimate the derivative. You can also pass in explicitly what is the analytical function for the derivative. Non-convex, we'll talk about non-convex versus convex, but that basically says how many local minima can be in your function for Newton's method to work. And Newton's method does not tolerate local minima well. And you can use it by using the Python Newton command. Okay, so that's our first optimization method. And it's very similar to all the other ones. They take in a function and it either minimizes or finds zeros of the function, and they almost all take in a starting guess. So that's sort of the two things that you have to pass in for any optimization. So are there any questions on Newton's method or optimization so far? All right. So let's look at maybe a more sophisticated example here. So let's say I want to integrate e to the minus s squared from 0 to x, and I want it to equal 1/2, and I want to find x. So this is kind of a this maybe should be a little bit familiar to you. Does anyone know what e to the minus s squared? What uh, what function have we been working with in the class that has an e to the minus x s squared pattern? Does anybody know?
The normal distribution.
That's right, the normal distribution. And what we're doing here is we're finding where does an integral of the normal distribution equal 1/2. So we're trying to find an interval that equals 1/2. Now, this is not exactly normal distribution because there's a little bit of junk that goes in the front to make it normalized. But we're trying to find an interval that equals 1/2. So what is that similar to that we've done in the past in this class? Does anyone know?
Is it like a confidence interval?
Exactly. It's like a confidence interval or a prediction interval. So this is when we're trying to find out the interval width that gives us a certain amount of probability. That's right. So this is actually a pretty meaningful example. And this could be done with root finding. Basically, we can move this minus 1/2 over to the other side and then make it equal to 0. So let's see an attempt to do this. Okay, so this is kind of a motivating example, and then we'll talk a little bit about debugging. But I think this is still, we'll come back to the example and solve it uh, in a moment. But let's see this first attempt. So we didn't talk about it, right, because we didn't have time, but I will just tell you that to do numerical integration, you use the quad function. The quad function, it's short for Gaussian quadrature, which is a way to integrate functions numerically. So the way the Gaussian quadrature function works is that you call quad and you put in the function you want to integrate, again using a lambda function. Then you put the bounds, so 0 to x. So we have our integrand and we have our bounds 0 to x. And notice x is unspecified, right? So we put this thing in a function as well, which I've called equation. So basically, equation takes in x, and then it calls quad, which integrates this integrand from 0 to x. Then I call Newton on my equation. So I have a function within a function which has an anonymous function. So then I call equation, or Newton on equation. So then it should find when this equation is equal to 0. However, there is a mistake in this code. It says can't multiply non-int of type float. Can't multiply sequence by non-int of type float. And it's appearing somewhere inside of this function. So this is actually really challenging to just read the message and identify what is wrong. Um, but that's what we're going to do in this lesson is we're going to try to find out what happened here. So here are the sort of the steps for debugging code. So step number 1 is basically correct any Python errors. So if Python's telling you something is wrong, obviously take a look at that line and fix it. But if you're still having an issue, restart the kernel because you could have old variables floating around or old functions to find. So that should be step number 2. Then correct any additional Python errors, right? Because once you restart the kernel, you may find additional Python errors. And then step 4 is to print to discover logical errors. So logical errors are when your Python code is valid, but there's a logical mistake in it. Okay. So what are some common mistakes for code? Copy pasta, leaving in old variables. This is probably the most common thing I see when I grade student homeworks and exams is that they copy an example from the lecture notes and it has different variable names and that messes up their code. The other example is mixing NumPy arrays and for loops. Basically, if you're using NumPy arrays, you should almost never have a for loop. And if you're using for loops, you should almost never be using NumPy arrays. So you should only, using your for loop should only be iterating over like ranges or lists and not arrays. Another example is just forgetting the order of function args and what functions return. So I'll just mention this example here. This example, the mistake with it is that quad doesn't return the value of the integral. It returns two things. It returns the value of the integral and the error associated with the calculation. So that was the mistake here, but we'll come back to that in example in a moment. But basically that's another example is forgetting order of function arguments and return values. Okay, so let's go into this a little bit deeper. So quad, Newton, minimize, so they should all take in an anonymous function that takes in one argument and returns one argument. So this lambda thing, this example here, this is not valid for quad or minimize or root because those have to take in a function that takes in one argument, and this function takes in two arguments. Okay. So let's see some examples of how to write these things correctly. So you can either define a function and pass it in by name, or you can do this anonymous thing. Okay. So these are two examples to the function x squared minus 3x plus 2. You can define a function, or you can do an anonymous one. So let's see these two examples. So I'll just do this here. So you could do this or this, and let's just do root finding here. So you can do Newton of version 1. You can put the name of the function in, or you can do the anonymous version. Either way is acceptable, either way works. Okay, I'll give you the same answer. So you can either define the function, then pass it in by name, or you can define it anonymously using the lambda keyword. And then another thing I just show here is that you can also use the numpy vectorize, which we saw before, which makes your function work with numpy. Both of these functions work with numpy, both versions here, but sometimes there are functions which do not work with numpy, like if you have a Boolean statement or something. So don't forget to use numpy vectorize if you want to call minimize or root finding on a function with Boolean statements. Okay, here's another example, okay, of a function. So here we're integrating from pi to x, sine squared of s ds. So the quad function returns two things. Like I said, it returns the value of your integral and the uncertainty of that integral. So we only care about the value of the integral, right? So this is how you correctly treat an integral, is that you get back the value and then the error, and you can basically, almost always we throw away the error. I mean, maybe you care about it if it's a very complex integral, but usually the error is very, very small. So in this example, we wanted to integrate sine squared from pi to x, and I've just called my function on 2 pi, so I'm integrating from pi to 2 pi sine squared of s. Okay, it's a little bit complicated, but basically, you have defined your integrand here using an anonymous function, then the bounds, and your upper bound is a variable x. So then in your function, when you pass in x, this gets set to an actual value, and then you can compute the integrand, or the integral. Okay, so any questions so far on these examples of defining functions?
So I have a very quick question. So if we go back to the code, like the one we wrote,
Yeah,
yeah, the first cell.
yeah.
So when we should have like two outputs because you get one output from lambda and one output from the function. Why didn't we only get one output? Like,
You mean in the bottom? Like that?
okay, yeah,
Yeah,
yeah, yeah.
yeah. Yeah, so Python or in Jupyter Notebooks, only the last line is output by default.
Mhm. Okay, yeah, makes sense. Okay.
Good question. Any other questions? Okay, so here is another example of writing a function. So let's say I have two vectors, x and y. And let's say that I have one component of x, which is a variable. So I have one component of x, which is changing. And I want to know what's the distance between vectors x and y as this one component changes. So I can define a distance function that computes the distance between two vectors. It takes in two values, x and y. And by the way, I didn't say this, but the goal is I want to convert this to a function which takes in one input and gives back one output, right? That's how we want to write our functions if we want to do minimization. Okay. So I first of all define a function called distance, and distance takes in two vectors and gives the distance between the vectors. Now this obviously doesn't satisfy the constraint of taking in one input and giving back one output. So then I additionally have these other, I have a second one, and I didn't state in the problem prompt, but basically I have here that x is 2, then the variable which is changing, then minus 3.5, then y is 1, minus 3, and 0. So y is a constant, and x is a constant except for one component is changing. So then my input is basically the value of that changing component s. Then the output, I call that function distance to get my one output. So then my distance function takes in one input, the value of the y component for x. Sorry, I shouldn't say the y component, the second component of x. And then it outputs the distance between x and y. So this is just another example of how, as long as your problem statement is taking one value, you just need to convert it so your function is taking one value and giving back one value. Now you may be wondering, can you do multiple dimensions? And yes, we'll see in a moment how we can do multiple dimensions by still only taking one input and giving back one output. Obviously, we use arrays to do that. So basically, we're always going to be taking one input, one output, even if we're in multiple dimensions. We just do that by making the one input an array. Okay. So I have here a couple examples of mistakes that are often done when people try to write functions for minimize or quad or root or Newton. Here's an example of not having a return value. Okay. So you need to put, if you're going to define a function this way, you need to put the statement return, because otherwise, it just returns none by default, which is not good. Another example that we saw in our original motivating problem was quad returns two things, the answer and then the error in the answer. So that returns two things, but we can only return one thing, right? We only want to be returning one thing when we're using minimize or root or quad. So we need to fix this function to only return one value. Another one, too many arguments. So we always want to take in one argument when we're using minimize or root or quad. So this example takes in two arguments, so that won't work for us. Okay. So that was kind of a digression about examples and common mistakes when writing functions for minimize, for optimization. So let's go back to this problem here. So I have here the integral of, again, 0 to x e to the minus s squared ds equals 1/2. And now I have fixed it so that I have, I correctly treat the output from quad to be two values, and then I only return the value of the integral. So then I call Newton on my equation. By the way, I don't know why this is here. You could just write equation. I will go back and fix that. I will go back and fix that. I guess I just was being redundant. Anyway. So, but the answer is still wrong. The answer is still wrong. Okay, so it turns out the integral from 0 to x, where x is 0, does not equal 1/2, right? And you guys should recognize that, right? If you do the integral from 0 to 0 of anything, it comes out to be 0. So I didn't solve my equation, right? This is not solving this equation. So what's wrong with my code here? Why am I not solving this equation? Somebody
Do you
have a
have to
thought?
subtract 1/2?
Exactly. Thank you. Yes. You have to subtract 1/2. So I needed to subtract 1/2 right here. Okay. So I did it here, the way I did it in this example here, that's why I did the lambda, is that I kept equation being this left-hand side, then I use lambda to create the left-hand side minus 0.5. So that's why I had a lambda x here. Okay, so now I've subtracted 1/2 from it, and now indeed I get the right value, x, so that the integral from 0 to 0.55 of e to the minus s squared equals 0.49999999994, so approximately 0.5. Okay, so I have solved the equation. So basically I have, taken this equation to represent the integral of 0 to x e to the minus s squared. So then I created an anonymous function, which is that minus 1/2, and found the root of it to solve the expression. Okay, any questions on this example? Great. Okay. So I didn't have a great place to write this one down, but I just want to cover scope. So scope is basically uh, the set of variables and functions which are currently defined and accessible. So in your code, at any given time, scope basically says which functions and variables do you have. And scope is indicated by indentation in Python. So right here I have basically two variables defined, x and y. So at this point in my code here, like right here, the things within my scope are x and y. Now scopes nest. So if I have like a function here called scope example, inside of this function, I have access to z, but I also have access to x and y. Okay? So when I define my function, I can still access things outside of my function because scopes nest. That is, this scope, which is, the indentation indicates the scope. This scope here, this indented scope, has access to things outside of it. So another thing about nesting is that inside of my scope, if I make my own variables, they disappear when I leave that scope. So here, this function, scope example, I say y is equal to 25, but outside of here, y is equal to 2. Then when I leave my function, even if I call my function, y is still 2, because this modification of y being equal to 25 only exists in this inner scope. Okay, so basically, if you modify variables inside of a scope, a scope that is more indented than the outer scope, it doesn't modify these variables. Now there is one kind of, I don't want to say it's an exception, but one thing about Python is that if you have a variable if your variable is a list, and you modify elements of the list inside of a scope, those modifications are permanent. And the reason why is that basically y is this list. So we're not changing what list y is equal to. We're just changing the inside parts of the list. So here y is a list. Then in here y is still a list. I'm not changing that it's equal to a list. I'm just modifying pieces of the list. So it doesn't violate what I just said about scope. Just if a variable name is it's equal to some kind of a list or an object or anything that's modifiable, you can modify pieces of that, and that's permanent. But if I were to say that y equals, a new list, that would disappear after I leave the scope. Okay, any questions on scope so far?
If you were to return the value of y in your function, does that mean that it also changes value outside of the scope, of the nested scope?
It would not, unless I put y equals here. So let's see the example that was asked, is that if I had this code here, and let's say I did return y would still not change. So y was 2, then inside the function y became 25, and then after the function y was still 2. But if I did this, then yes, it would change, but not just returning it. So returning y doesn't do anything to the variable outside of it. Good question. Any other questions? Okay, so things to remember about scope is that they nest, so you can access things that are outside of your scope as long, if it's less indented. And then you can modify variables. So that's what we saw in this other example, is that we can modify variables inside of inner scopes But anything you create inside of your inner scope will disappear. Okay, so just anything you create will disappear. So like if I created another variable called z in here, and I tried to print out z, it would not exist anymore because it was defined inside of this scope. But then we left the scope, so it's not around anymore. So it's not defined. Okay. So let's go back to optimization. So are there any questions about scope before I move on? Okay. So I think actually we can take a 3-minute break. I think I could just pause the recording. And I'm going to refill my coffee, and you guys can just go ahead and take a little break before we come back. All right, did anyone think of a question during our break? No? All right. So we're going to return now to optimization. So we just saw a little bit about scope. So we're going to dig a little bit more into optimization. So what is optimization? So optimization, like I said, is when you minimize a function, or you find the roots of it, or you maximize a function. And optimization is used to solve nonlinear equations. So we saw cosine of x equals x, like that's an example of a nonlinear equation we can solve with optimization. Optimization is a way to solve systems of equations. You may have learned in linear algebra, and I think we saw in this class that you can do things like matrix inverses to solve systems of equations. But that only kind of works if you can rearrange them to be like a linear product of coefficients and variables. Optimization is the general way to solve systems of equations, even when you can't rearrange them into being like a matrix product. Optimization is also used to solve equations with constraints or without constraints. So if you wanted to solve an equation like say cosine of x equals x, but you want to restrict it so that x is less than 1, right? Like that's an example. Or let's say you have two equations, and you want to make sure that x plus y always equals 1, and you want to find solutions for that. So optimization is how you add constraints. And sort of, the goal is a lot of times optimization is how we take a equation that we think describes data, and it allows us to fit that equation to data. So optimization is how we do model fitting at the end of the day, which is one of the most common, goals of numerical methods and statistics, is to come up with a model that describes your physical process. So optimization is a pretty powerful technique and something we like to use a lot. So the steps that we think about when doing optimization is we think about, are we doing 1 or n dimensions? Are we minimizing or root finding? Are there constraints? Are there bounds? So constraints means you have some kind of uh, expression that has to be satisfied to found a solution. Bounds means you just have some kind of, some restraint on what your x value can be. And then is it convex or non-convex? And we'll come back to this in a minute, but that's the last thing you want to think about. That kind of means, are there a bunch of local minima or not? So convexity. So yeah, we're coming to it now. So it's weird, but we say convex and non-convex, and it has nothing to do with concave or convex. So a non-convex means that the function has multiple minima. And then a convex function means that it has basically, it's like a convex function. There's just one minimum in it. So how do we identify convexity? There is no good way. Basically, how do you identify if your problem is non-convex? You plot it. You can also just start trying to do optimization and see if you have different results. Like, does your optimization get trapped in local minima? And then the last time is sometimes you just know from the equation or just know from looking at the problem that it's a non-convex problem. So identifying if something is non-convex is not just a Python function call we can do, or it's not just some kind of calculation you can do. It requires you to have some understanding and insight about your optimization problem. So let's see some examples. So here's an example of a function with two wells. Okay, this is a function that I've just plotted from -4 to 4, and there's two minima, right? And one local maximum, and there's probably maxima on either left and right. So this is an example of something which is non-convex because there are local minima, or multiple places where the derivative is equal to 0. In fact, it's even worse than that because there's a spot where the derivative is undefined, right? Okay. So how would you know this is non-convex? Well, you could look at how I defined it, right? Like it's defined with an if statement in the middle of it. So it's a piecewise function. So if it's piecewise, it's going to be non-convex. And then also the plot allows you to identify it. Okay, so are there any questions on non-convex functions? I think, basically we're going to see some examples, but that's sort of the lesson, is that you identify something as non-convex by plotting it and looking at the equation and trying to think about if there's multiple places the derivative can be equal to 0. Is there any questions on that? Okay. So the gold standard, the best way to optimize for minimization, the best way to minimize or maximize, the go-to optimization method used everywhere, like this is what's state of the art in research and industry and engineering, is BFGS, the Big Friendly Giant system. It actually stands for Broyden, Fletcher, Goldfarb, and Shano, which are 4 people who developed BFGS optimization. And it is for continuous problems, arbitrary dimensions, and I think it works for bounds, but I think it doesn't work for constraints. Actually, I think it works for constraints too. No, it doesn't work for constraints. I think it works for bounds. And it does not necessarily work on non-convex, but basically it's what's standard. Like if you ever have an optimization problem, minimization problem, this is the first thing you try. And in Python, you just call it by calling minimize because, like I said, it's a gold standard. So if you call minimize in Python, then it will use this method. So BFGS, standard method. So just some nomenclature here. That function that we pass in to minimize is called the objective function. Okay, so when we were doing root finding, like with Newton, we just called it the function. But here, people call in minimization the function, they call it the objective function because the objective is to make it as small as possible. So let's see an example. Here is an objective function, x squared. Okay, everybody knows x squared. I plotted it for you. So is this non-convex or convex? Does anyone want to tell me if this is non-convex or convex?
Convex.
Thank you. It is convex. So it's convex because there's only one place where the derivative is equal to 0, down here. So to call minimize, I import it, then I call it on my function, and I have a starting point. So again, we have to give a starting point. And it gives you a whole bunch of output. The reason why it gives you a whole bunch of output is minimization is not always easy. So let's see a few of the output things. One of the things is it gives you a message. The message is always good to see. So it says the optimization terminated successfully. So that says that the optimization went well. Then it gives you at the top here the value of the function. So we're trying to minimize, so we should see a small value here. So it says 2.54 times 10 to the minus 16. Now, what is the minimum for x squared? Should be 0, right? So, it didn't succeed all the way, right? It's 10 to the minus 16. It could have been smaller, but that's how optimization works. It's a numerical method, so it never gives you like the exact answer. It always just gives you the best approximation it could get. The Hessian inverse and the Jacobian, these are just some diagnostics on it. How many times it called the function, how many iterations it did, how many times it had to calculate the Jacobian, which is the derivative. The status, basically 0 means it succeeded. Then success is true, means it succeeded. Then here's the actual value of x that gave you the optimal, the minimum value of the function. So in this case, it's 1.59 times 10 to the minus 8. What is the optimum for x squared? Well, it's x equals 0, right? But, it did a pretty good job. So here I have more details on what each of these things mean. So, like I said, we want to use convex functions for minimize. One thing to be careful of is that you don't necessarily want, I shouldn't say maximum, I should say minimum. So when we're minimizing the function, we don't really want the minimum to be at minus infinity or infinity, because then basically our result will be a very, very small or very large value. Let's just see an example. Like, let's say I wanted to minimize this function. So this is a good example. Does anyone know what this function is? I think it's the equation for a ellipse. I don't know if anybody remembers their pre-calc from high school, but I think this is an equation for an ellipse. Maybe not, though. I don't know. Here's a plot of it. No, I think this is just a parabola. I think if it was x and y, it would be an ellipse. Anyway, this is the function. So this is an example of, again, a convex function with a good minima. You can call it. And here I've showed you how to print out this object. So remember in the first example, minimize gave us this result with lots of things like the success, the message, stuff like that. You can access the value of x by using result.x, and you can access the value of the function with result.fun. And so it said that the value of x that is minimal is 3.33, which indeed appears to be correct. And it says the value of the function at that point is 0.667, which indeed looks to be correct. So here's an example of a bad objective function. So this is that what I said above is that we want to make sure our minimum isn't at infinity or minus infinity, because then it's kind of a silly example. So let's minimize x minus 4 divided by 2. So what is the minimum of this function? Well, it's minus infinity, right? So when I call minimize, minimize basically will just keep trying, and then eventually it'll just decide to stop. So it says that the minimum occurs at minus 1.8 times 10 to the 8. Now this is not the true minimum, right? Like this is just as far as it went before the number of iterations gave up. And it says the function value is this. So the true minimum is at minus infinity, but basically it never made it all the way. Okay. So are there any questions thus far on minimization? Okay. So one thing we haven't talked about is the starting point x naught. So I just said, you can start wherever you want. So let's take a look at this function. We want to minimize this function, 4 times r to the minus 12 minus r to the minus 6. Does anyone know what this function is? This is a very famous function from chemistry. Anyone want to have a guess? So this is the Lennard-Jones function that describes van der Waals forces between atoms, or between, molecules in an ideal gas. So if I were to try to minimize this, okay, so I've entered in the function here using a lambda. If I were to try to minimize this and start at x not equals 0, it says the minimum is 0, and I get a bunch of runtime warnings. Can anybody tell me why I'm seeing runtime warnings if I start at x not equals 0?
Is it not defined at 0?
Yeah, that's part of it's not defined, but what is the more, what is the mathematical mistake that's happening?
Dividing by 0?
That's right, dividing by 0, yeah. So you're both right. Basically, it's not defined, but it's more like 0 is not in the domain, right? Because we can't divide by 0. So I know this is kind of, in retrospect, it's obvious, but a lot of people will make a mistake by starting at 0 just as a default, because a lot of times 0 makes sense, but actually 0 is sometimes not in the domain because you're dividing by the value. So, always think about that whenever you choose your initial values. Make sure it's in the domain. So if you were to plot this function, you would see it looks like this. So you can see 0 is not in the domain, right? Because it just keeps going up and up and up, but it hits infinity at 0. So then if you start at 1, which is a reasonable value, 1 is right here, you'll see that the minimum is at 1.12. Okay. So I know this is kind of obvious, but it's always good to remember this, is that if you ever want to minimize a function, you can just, sorry, if you ever want to maximize a function, you can just minimize its negative. So like if you wanted to maximize the function minus x squared, you could just put a minus sign on it. Okay. It's kind of a weird example that I chose to have the example have a minus sign. So then you put a minus sign on it. I don't know. Anyway, so if you ever want to maximize, all you do is you put a minus sign on your function and then you minimize it, and that will find the maximum. So in all of the nomenclature, when people talk about optimization, everybody will be always talking about minimization. Like people will talk about how to minimize, this is a method for minimization and stuff. And some people will be like, oh, Professor White, I found all this stuff on minimization, but I couldn't find out how to maximize a function. It's because we all just know, or it's just, everybody knows the trick is that you just put a minus sign and minimize, and that gives you the maximum of the function. So all of the nomenclature discussion, and when people talk about optimization, it's always about minimization. So that's just just an important thing for you to know. Okay, now before we go into multiple dimensions, are there any questions on what we've seen so far?
So do you recommend starting from 0, even though like, yes, it will give me some errors because we don't have like 0 in the domain, but at the same time, maybe we have a minimum value between 0 and 1. But if we started at 1, we're gonna miss the minimum value.
So the only, like if your function is convex, it doesn't matter where you start. You can start at -10, you can start at 10, you can start at 100, you can start at -2. It's fine as long as it's in the domain of the function. If your function is non-convex, then you have to start messing around with that. And we'll see an example later on. But yeah, if it's non-convex, then you could basically try 3 different starting spots and see if you get the same answer. And then, you're good to go if you do. So I would say it depends on the problem. Step 1, make sure it's in the domain. Step 2, try a few different ones to ensure that it's convex. Or if it's non-convex, then try a bunch and, take the one that gives you the best value.
Okay, got it. Thank you.
Yep. Interesting. I think that code is wrong. Okay. So to do multiple dimensions, all we have to do is make our function take in an array instead of a single value, and then we need to make sure to tell minimize that we're working on a multiple dimension problem by making sure x naught is multiple dimensions. So let's take a look at this, which I think is now an ellipsoid or an ellipse. So we have 2 variables, x and y. Probably that should say f of x, y. So the way we set this up is that we make our function still take in one argument, always going to take in one argument, but it's understood to be an array. So x is going to be the 0th element in the array, and y is going to be the 1 element in the array. Then I specify x naught to be a list whose elements are 0 and 0. So I'm starting at 0, 0. And then it tells me that the minimum occurs when we have a 4 and a -3. If I look back at my function, that makes sense. When it's 4 and -3, it should be 0. Okay, so that's all there is to it for multiple dimensions. You just make it, still you take in one argument, but you just index that argument like it's an array. And then you just make sure that your starting point is also an array or a list. So one thing that's kind of sloppy in our class is that although I specified x naught as a list, SciPy will convert it to an array for me. So I'm just kind of loosey-goosey here that x should be an array, not a list. But SciPy will upgrade it to an array for me, so I can just use square brackets here. So it's actually pretty simple to do multiple dimensions, so I don't really need to talk too much about it. So are there any questions here on how you would do multiple dimensions? Now the only thing is that we'll discuss it in a moment here, but still my output is one number, right? Even though my input is multiple my input is a multi-dimensional array, I'm still outputting just one scalar value. And that's how minimize always works. Minimize always minimizes a single output value of your function. Your function should always output a scalar. Okay. So always minimizes your function should evaluate to give a single number, but you can take in a multi-dimensional array for the input. So we're going to see another, just another example for identifying convexity. Just a few more examples here. So here's another example of something which is non-convex, right? There's a minimum at minus infinity and a minimum here. So minimum at minus infinity, that's a global minimum is minus infinity. There's a local minimum here. So it turns out that seeing this local minima can happen if your starting point is near it. So here I'm using minimize, and I'm starting at 0.005, which is right like here. And then it thinks that the minimum is at 0.41. So it thinks the minimum is right here. So it started here and it went to here. So it had this, this problem of finding a local minimum. And that's because minimize doesn't work well for non-convex functions. But one of the tricks you can do is you can basically start at a different spot and you'll see a different value. So here, if I started at minus 0.5, so I started over here, and it made it down to minus 1.8, which is, times 10 to the 8, which is basically minus infinity, made it very far. Okay, so starting in multiple locations can give you a clue of if it's a non-convex function. Okay, so it's just another example about that. So let's take a look at another method in optimization, and that's called the Pal hybrid method. So the Pal hybrid method is how we do root finding in multiple dimensions. So Newton works for one dimension, but Pal hybrid method works for multiple dimensions. So in the optimize, if you call root, it will do the Pal hybrid method. So we saw minimize uses BFGS, root uses the Pal hybrid method. So let's see an example. Like let's say we want to solve cosine x plus sine x equals x. I don't know if anybody's ever thought about this equation, but it looks like a fascinating equation to me. So how would we solve it? We would just call root. Okay. Then here's my function. So cosine of x plus sine of x minus x, and we want it to equal 0. I started with x not equal to 1. You could have started with x not equal to 0. But notice that root now looks a lot like minimize. Like, remember Newton just gave us one number, but now root gives us another sort of complex, the solution has converged. How many function evaluations did you get? What is the radius of convergence? What's the status? Was it successful? True, right? So it turns out 1.258 solves the equation cosine of x plus sine x equals x. I don't know if that's some kind of multiple of pi. Is that pi halves? No, it's not pi halves. I don't know what that... Does anyone know the significance of 1.258? Or is it just some numerical coincidence? I don't know. Anyway, I guess we'll find out another day. So another use for the Pal hybrid method is for solving systems of equations. So if you have an expression like 3x squared minus 2y equals 4 and x minus 4y squared equals minus 2, you can rearrange that to be a system of equations, and you want them to all equal 0. So now this is different. So minimize, we saw we could do multiple inputs, but we still had one output being 0. Now we're going to have a multi-dimensional input v, which is going to contain our x and y, and a multi-dimensional output, which is going to be the value for equation 1 and equation 2. And we're going to set all the equations equal to 0. So basically v comes in, and x is going to be the first element in v, and y is the second element in v. Then I compute my two equations, where I've rearranged them to be equal to 0. So I put the 4 on this side and the 2 on that side. And then I return back a multi-dimensional array. And then root will find the solution where both equations are equal to 0. So this is not an easy equation to solve. 3x squared minus 2y equals 4 and x minus 4y squared equals minus 2. I would challenge you guys to solve that by hand. It's not easy. And yet here we can solve this. So, I mean, did anybody know how to solve equations like that before this? I guess you could maybe enter this on your TI-89, but this is a nice way to solve it in Python here. And it turns out the answer is x equals 1.4 and y equals 0.92. So this is different, right? So minimize, we had a multi-dimensional input, but we always had to have a single dimensional output. But with root finding, you can have a multi-dimensional input and a multi-dimensional output. Okay. So are there any questions on this example? Okay. So just one kind of note here is that you should always pay attention to the messages. Okay. Look at this message here. The iteration is not making good progress as measured by the improvement from the last 10 iterations. So this message tells us that, and you can see the success equals false. So this is something dangerous about optimization methods, is that they still give you an answer. Like you could still get an X value and think that it worked. But if you don't look at the message and you don't look at the success, these are not actually correct. So if you were to actually, did I print it out? I don't think I did. Anyway, but if you were to try to plug these into your equations, you would see they are not solutions. So you can't just blindly take what you get back from root or minimize. You need to actually look at the message and the success flag to make sure that it worked. Okay. So why did it fail in this case? I think with this x cubed, I think there's no solution to this system of equations, and that's why it failed. So there's no solution here. So it's not obvious from looking at it, but you'll see from the message if there's likely no solution. And here, just these are very long, right? Like I have comments here and I define the function. You can still write that on one line using a lambda function. This is just me showing you what it looks like in one line. So right here I have a list, and the first element in the list is the first equation, and the second element in the list is the second equation. All right. So you can write this very compactly. Oops. Just a side note about this system of equations, there are two solutions. There are two roots. So it's an example of a non-convex function. And if you start at 0, 0 versus you start at 1, 1, you'll see two different root solutions. So this is also a solution to those system of equations. And that's just because we have a square in there, you can have the negative instead of the positive root. Okay, so are there any questions on this multidimensional root finding examples?
Is there a way to get all solutions to the equation?
Nope. Nope, there is no way to get all solutions. I mean, this comes back to non-convexity, is that in the branch of mathematics, there is no way to identify the number of local minima in a function, except numerically. So there is no analytical way to just look at a function and determine how many roots or local minima it has. This is actually an open problem in the branch of mathematics. So there is currently no way to solve that. So basically, you can just try multiple starting positions. You can make a plot, and that's basically state of the art for determining how many local minima or roots are in your function. So if any of you think mathematics is a boring field with nothing left to do, here's an example of something in our everyday lives that is currently impossible because the mathematicians haven't solved it yet. Any other questions? Okay, so that actually concludes all we will cover of Unit 11 this year. So like I said, we had to cut out some of the lectures. So we're going to skip Lecture 2. And Lecture 2 basically shows you how to add constraints and bounds. So in these minimizations and root finding, we didn't have any constraints or bounds. So if you ever need to do constraints or bounds for optimization in your projects or in your coursework in your class, take a look at the notes for Lecture 2, and that will show you how to do the constraints and the bounds. But I think this is most of what you will need to do, which is doing optimization or minimization. And another thing about the bounds is that bounds give you the capability of turning non-convex function into a convex function. So for example, one of the functions we saw over here, this function here, this could be made into a convex function by bounding it to only be from here to here. Then we'd only have one local minimum. So bounds are actually kind of nice to clean up functions that are basically non-convex. So bounds is kind of a good thing to know as well. But you can look at the notes and it's not very complicated. Most of the work in this unit is from this lecture here. Okay, any other questions? Okay, so I'm going to go ahead and stop